Bismillahirrahmanirrahim. Assalamu alaikum viewers. In today's lecture, we will be discussing tokenization, morphology, and text normalization. How computers read words. One of the central points that I want you to understand from the very beginning is this. What seems simple to us, a human being, is not simple for a machine. Let me ask you a very simple question. What is a word? A common man can tell you that a word is a unit of language. But here is a surprising truth. A computer does not know what a word is, not unless we tell it explicitly what a word is. And telling a computer that it can find every word in every kind of text in every language turns out to be one of the most interesting and challenging problems in all of computational linguistics. I want to give you three simple examples to show what I mean. Example 1. In English, the sentence I don't know contains a contraction don't. Now, is that one word or two words? Most people would say it is two words squeezed together, do and not. But in the written text, there is no space between them. So how does a computer know where one word ends and another begins? The second example, in Urdu, and this is directly relevant to us, words are written in Nastaliq script in a flowing cursive style. Some multi-word expressions look like a single continuous unit on the page. So the rules for where one word ends and the next begins are far more complex than in English. How does a computer handle this situation? The third example, consider the word running. In a dictionary, the base form is run. If a computer is searching for all mentions of run in a text, it needs to know that running, runs, rain, and runner are all related forms of the same root word. But how does it make that connection? How does a computer know that running is not completely different from the word run? These three questions, where do word begins and where it ends? How do we handle different written forms of the same words? And how do we clean and standardize text for machine processing are exactly what today's lecture is about. Today, we are covering lecture how computer read words, tokenization, morphology, and text normalization. This lecture has 5 parts. Part 1 covers tokenization, the process of dividing text into individual units. Part 2 covers text normalization, the cleaning and standardization of text before analysis. Part 3 covers morphology, the structure of words and how computer processes it. Part 4 covers stemming and lemmatization, 2 key methods for reducing words to their base form. And part 5 is our full practical demonstration in Python and NLTK. By the end of this lecture, you will understand why reading words is harder for a computer than it sounds. And you will be able to apply these tools in your own research. So let's start. Part 1, tokenization, dividing text into units. What is a token? Before we can do anything else with language computationally, before we can take parts of speech, parse sentences, or train a language model, we need to convert a raw text into a sequence of discrete units. These units are called tokens, and the process of producing them is called tokenization. Now, a token is not always exactly the same as a word. This is an important distinction. In most NLP systems, tokens can be words, punctuation markers, numbers, symbols, or even fragments of words called subword units. But for now, let's think of tokens primarily as words and punctuation markers. Why? because that is the most common level of tokenization and the one you will encounter most in your research and studies. The formal definition of a token is a meaningful unit of a text, typically a word or a punctuation mark, produced by dividing a continuous text string into discrete segments or units. Now you might ask, why do we need a special process at all? Why can we not simply split text at every space? And this is exactly the right question to ask. Let us see what goes wrong if we do it. Why simple space splitting fails? There are 6 main problems with simply splitting text at spaces. The first problem, punctuations attached to words. In English text, punctuation markers are typically written directly adjacent to the words with no space. The word university in the inverted commas at the end of a sentence has a period attached to it and 2 inverted commas attached to it. And if we split at space, we get university as a single token. But for most purposes, we want university and a full stop or the inverted commas to be treated separately in NLP. This is the first problem. The second problem is contractions, which we already discussed, but let's discuss it again. English contraction like don't, can't, I'll are written without spaces but represent 2 grammatical words. They are compressed into one written form. For grammatical analysis, it is usually important to separate these 2 different contracted forms, and this is a decision you must make based on your research question or research purpose. The third problem is abbreviations and titles. Periods appear both as sentence final punctuation and with abbreviation. For example, dr dot doctor contains a period but is not a sentence boundary. USA contains multiple periods but it is a single token. Now, do we treat period as a separate unit, or do we? The fourth problem, numbers and special format numeric expressions like 3.4, 5000, the dates and the percentage all contains non-alphabetic characters that carry separate meanings. A tokenizer need to recognize these are unified tokens rather than splitting them at every punctuation mark. This is another problem. The fifth problem is the hyphenated words. English uses hyphens in compound words like well-known, in prefixes like non-standard. Whether a hyphenated expression should be 1 token or 2 depends on the linguistic judgment and application needs. The sixth problem is social media and the digital text. Modern text includes hashtags, mentions, URLs, and emojis. These require specialized tokenization rules that general purpose tokenization may not handle well. For researchers studying online discourse, Pakistani Twitter, WhatsApp groups, conversation, this is especially important for them to understand this type of tokenization. Now, one of the special challenge is the challenge of Urdu and Pashto tokenization. This is directly relevant to the students who are working on comparative analysis in the English syntax or lexical analysis with Urdu or Pashto. Everything I have described so far applies primarily to English. For Urdu and Pashto written in right to the left scripts, the problems are significantly more complex, and I want to pay close attention to this because it is directly connected to your research if you are doing a comparative study. Urdu uses the Nastaliq style of Arabic script. Letters in Urdu are connected in flowing cursive form, and the rules governing where connections occur and where they break are both linguistic and calligraphic. Additionally, Urdu text in digital context is often written in multiple ways. The same word may appear in proper Urdu script, in a formal documents, in romanized Urdu, in SMS and social media, or in the mixture of both in the same text. This code switching creates tokenization problems that have no parallel in monolingual languages. For Pashto, the challenges are even greater because NLP resources are more limited in this language, and many tokenization tools developed for Arabic or Persian scripts handle Pashto imperfectly because of Pashto specific characters. I am raising these issues not to discourage you, but to alert you when you used to understand NLP tools and Urdu or Pashto text, you should expect tokenization errors. You should develop the habit of manually examining samples of your tokenized output to assess the quality before drawing any analytical conclusion on that data. Now let's discuss the different types of tokenization. How do NLP systems actually perform tokenization? There are three main approaches. Approach 1, rule-based tokenization. The simplest approach is to write explicit rules, split 8 spaces, then handle known exemptions. Rule-based tokenizations are fast, transparent, and easy to understand. Their weakness is that they require extensive manual work to cover all the edge cases of a language. The second approach, statistical tokenization. A statistical tokenizer is trained on a manually tokenized corpus. It learns probabilistic rules about which character sequences tend to be token boundaries. Its weakness is that it requires training data, and for a low resource language like Pashto, sufficient training data may not exist. The third approach, subword tokenization. The modern large language models, including ChatGPT, Claude, Gemini, or other similar systems, use a different approach entirely. Instead of dividing text into whole words, they divide the text into subword units. The word tokenization might be divided into tokenization. This approach means the model can handle any word, including word it has never seen before, by combining known subword pieces. The most widely used method are byte pair encoding (BPE) and word piece. For the purpose of this course, we will primarily work with the word level tokenization using NLTK because it is the most interpretable and most directly connected to the linguistic concepts you already understand. Now we should discuss text normalization. This is another important part of this lecture. After tokenization, the next step in most NLP pipelines is text normalization. And the central point here is simple. Normalization means converting text into a standard, consistent form, removing or correcting variation that do not carry meaning, but that would cause a machine to treat essentially identical thing as a different. Think about it this way. If you are building a search system and a user types Pakistan with capital letter, then Pakistan with small letter, and Pakistan all capital letters, they are asking for the same thing. But a machine that treats these as three different strings will give inconsistent results. Normalization ensures that these three forms are treated as one. Text normalization is the process of converting text into canonical, consistent form by removing or standardizing variations that do not carry meaning for the task at hand. Now, the key phrase in this definition is for the task at hand. What counts as a meaningless variation depends entirely on what you are trying to do. The right normalization choice depends on your research purpose, and this is a decision you must make consciously and carefully. Now let's discuss the main normalization steps. The first step, case folding. Case folding means converting all text to a single case, usually lowercase. So there is no capitalization. This is the most basic normalization step and is appropriate for most information retrieval and frequently analysis tasks. However, case folding lose information about proper nouns, and that matters for named entity recognition because apple, the company, and apple, the fruit, are different things. Now step 2, removing noise. Raw text often contains elements that carry no linguistic content. For the purpose of analysis, HTML takes leftover from web scraping, XML markups, headers, footers, page numbers, formatting characters. These all are extra things. Before linguistic analysis, this noise should be removed. The specific steps depend on your data source and why do you need it. The third step, handling numbers. Numbers can appear in many forms, for example, in 1000 written as words and written as numbers. Depending on your task, you may want to normalize all of these to a single representation, perhaps the digit form 1000, or to a general placeholder like num, that simply marks the presence of a number without preserving its value. Then step 4, expanding contractions. For some NLP tasks, it is helpful to expand contraction to their full forms before analysis. Don't become do not, I'm become I am. This is particularly useful when the downstream task involves syntactic parsing, because parsers are typically trained on the formal text where contractions are rare. Step 5, handling special characters. For Urdu and Pashto, the equivalent issue involves the optional diacritical markers, harakat, that indicates vowel sounds in Arabic script languages. In most Urdu texts, these are omitted, which creates ambiguity that tokenizers and parsers must handle. This is another area where standard English NLP tools need to be used with caution. Step 6, sentence boundary detection. Identifying where sentence begins and where it ends is a task that can be carried out through normalization. The main challenge, as we have seen, is distinguishing sentence final periods from periods within the abbreviations. Now, you must take care of all these punctuation markers. These are the different steps that you follow in the process of normalization. Now, I want you to understand something important. For a PhD researcher in linguistics and literature, normalization decisions are not merely technical, they are analytical choices that shape what your data looks like and what conclusions you can draw from your data. If you are doing a frequency analysis of vocabulary items in Pakistani newspapers, editorials, you need to decide, do you case fold? If you do, you lose the distinction between proper nouns and common nouns. If you do not, THE as capital and THE and small letters are counted separately even though they are the same word in different positions. These decisions should be documented explicitly in your methodology section, and you should write like texts were low-cased and contractions were expanded before analysis. This is the kind of statement that you will need to incorporate in your research methodology. Now let's discuss the computational morphology, which is the next part of this lecture. Morphology is the study of the structure of words, or how words are formed in a language. We can also say that morphology is the study of morphemes, and morphemes are the smallest meaningful units. We do have two kinds of morphemes, free morphemes and bound morphemes. Free morphemes can stand alone, while bound morphemes are attached to the free morphemes. For example, ed, ing are bound morphemes, and these are attached to the verbs. Now let's discuss morphology and computational linguistics. Morphology creates enormous variability in the surface forms of words, and this variability is a major problem for machines. Consider the English verb teach. This verb might appear as teach, teaches, teaching, taught, or teacher. A simple string matching system will treat these as 5 completely different items and miss the connection between them. For a human reader, the relationship is obvious. For a machine, it must be made explicit. So this is the morphological variations that you must teach to the machine before going for any analysis. Now let's talk about types of morphological process. Inflectional morphology are inflections that modifies a word in terms of grammatical information, tense, number, person, or gender, without changing its basic lexical category or core meaning. For example, walk becomes walks, or walked, or walking, and all these are inflectional variants which is added to this verb. Inflection is relatively regular and predictable in English, which makes it computationally traceable. The main task for computational system is to identify the base form, the lemma, that underlies all these inflectional variants. Derivational morphology, on the other hand, creates new words, often of a different grammatical category from the existing words. Teach becomes teacher, a verb becomes a noun, happy becomes unhappy, an adjective is negated by a prefix, nation becomes national, and it can also become nationalize. It can also become nationalization. So derivation is less regular than inflection and harder to handle computationally because derivational relationships are often idiosyncratic. While discussing morphology, there is another important concept: compounding. Compounding compounds two or more free morphemes to create a new word. For example, blackboard, notebook, software, database. In English, compounds may be written as a single word, hyphenated, or two separate words, and the same compound may be written differently by different authors. This orthographic inconsistency creates tokenization and normalization challenges on the top of morphological ones while dealing with language as data in computational linguistics. In Arabic and other languages, a root typically has three consonants and it is combined with a vowel template to produce different word forms. The root katab relates to writing. Kataba means he wrote. Kitab means book. Katib means writer. Since Urdu shares vocabulary and morphological patterns with Arabic through Islamic borrowings, awareness of such morphological variations is relevant for the Urdu NLP as well. So keep in mind if you are working on such data. Let's discuss two levels of morphology in this regard. How do computational systems handle morphological analysis? The classical approach developed by Chemo in 1984 and still widely used today is called two-level morphology. The basic idea is this: every word form exists at two levels. The lexical level, which represents the abstract underlying morphological structure, and the surface level, which represents what is actually written or spoken. The system maps between these two levels using finite state transducers, a type of automation that transforms one string into another. Let me make this simple by giving you an example. The plural of fox is F-O-X-E-S, not F-O-X-S. At the lexical level, we have fox plus plural. At the surface level, we got fox ES. The two-level rule describes the insertion of E as a mapping between the lexical string and the surface string. Similarly, study plus plural studies, the Y at the end of the study becomes IE before the plural S. The power of this approach is that it works in both directions. And given a lexical form, it generates the correct surface form. Morphological generation. Given a surface form, it identifies the underlying lexical structure. Morphological analysis. This bidirectionality is very much crucial for NLP, for natural language processing. Now let's come to another interesting part of this lecture: stemming and lemmatization. It simply means reducing words to their base form or their roots, the pluralification of word forms, but they solve it in a different way, with different level of linguistic accuracy. If you are building an information retrieval system and a user searches for teaching, your system needs to return documents that contain teach, teaches, taught, teacher, and teaching, because all of these are relevant. If your system only returns documents with the exact teaching word, it will miss most of the relevant documents. To solve this problem, you need to reduce all these forms to a common root or a base form. And how do you do this? Through these two methods: stemming and lemmatization. Stemming is the faster, simpler, and cruder of the two approaches. A stemmer applies a set of rules to strip affixes from the words, prefix and suffix from the words, leaving a stem alone. The stem does not have to be a real word. It just has to be consistent representation that all related forms are reduced to it. The most famous stemmer for English is the Porter stemmer, developed by Martin Porter in 1980. Let me show you how it works on some examples. Take the word running, remove ing and you have run. Take the word happiness, remove ness, and you have HAPPI, not Y. Studies, remove IES, add Y, and then you have STUDY, study. Generalization, remove Asian, generalize, remove I's, and you have general. Notice that happiness produces HAPPI, not HAPPY, which is the actual base form. The Porter stemmer does not produce linguistically correct base forms, it produces consistent stems, consistent enough that all forms of happy map to happy HAPPI and can therefore be retrieved together. This is sufficient for information retrieval, where exact linguistic correctness is less important than consistency. On the other hand, lemmatization is the linguistically principled alternative to stemming. A lemmatizer reduces each word to its lemma, the canonical base form that appears in the dictionary, the base form that is available in the dictionary. Unlike stemming, lemmatization always produces a real word, and it uses both morphological rules and a lexicon to handle regular forms correctly. Lemmatization correctly handles was to be, not was as a stemmer might produce as wa. Better in relation to could, the comparative of an irregular adjective. Rain in relation to run, an irregular past tense. Mice is related to mouse, an irregular plural. And in the same way, children to child, another irregular plural. These irregular forms are not predictable by a simple suffix stripping or stemming. A lemmatizer handles them because it has access to the lexicon. There is one important complication. Lemmatization requires knowing the part of speech of a word to produce the correct lemma or the correct base form. The word saw could be the past tense of see, in which case its lemma is see, or it could be a noun referring to a cutting tool, in which case its lemma is saw, not see. This is why in NLP pipelines, parts of speech tagging typically precedes lemmatization. For your research in linguistics or in literature, lemmatization is most always preferable to stemming because you are interested in linguistically accurate base forms. However, if you are working with a very large corpus and computational speed is concerned, then stemming may be an acceptable compromise for initial exploratory analysis, not for the detailed linguistic analysis. Now let's come to the most difficult part of this lecture, and that is the practical demonstration through NLTK and Python. For this purpose, you will open the clean Jupyter notebook in Python with large font size there so that you can see it easily. We will work through 5 practical steps. First, we will tokenize text and examine the differences between a naive approach and NLTK's approach. Second, we will apply normalization steps. Third, we will apply the Porter stemmer. Fourth, we will apply the WordNet lemmatizer. Fifth, we will build a complete pipeline and apply to the real text a passage from any newspaper or anything you want to demonstrate the full workflow on the software. So step 1, tokenization. Let us begin by showing exactly why simple space splitting is not enough and what NLTK does differently. First of all, import NLTK. How will you do it? Import it from nltk.tokenize. Our test sentence is Dr. Bilal Khan, who teaches at Fata University, can't believe it's already 2024. He said the USA paper costs $1,500. Method 1. Split at spaces. Now write naive this dash then tokens is equal to test dot split and the parenthesis, And look at the problem in the output. Khan has a comma attached. University has a comma attached. 2024 has a period attached. Each of these is counted as single token even though the punctuation should be separate. And we have not correctly handled the contraction can't, or the abbreviation USA at all. The second method, now work through NLTK word tokenize. How do you do this? Now write NLTK dash tokens is equal to word dash tokens test in the parenthesis, that sentence. Print NLTK tokenization in the parenthesis. Print NLTK dash tokens in the parenthesis. This is much better. Khan is now correctly split into Khan and the comma. USA is correctly kept as single token. Now NLTK recognizes it as an abbreviation and does not break it at the internal periods. 2024 is correctly split into 2024 and period. The number and the sentence final period are now separate tokens. Come to the second step, text normalization. How we normalize text to get good results. Now let us build a normalization pipeline, a sequence of steps that clean and standardize text. We will apply it into a longer passages. Import the raw text. The raw text is: the Prime Minister's office announced on Monday that GDP growth has reached 3.5% in Q1 2024. Pakistan's economy, which couldn't recover fully after 2022's floods, is showing positive signs. Official said they allocated 200,000 for flood victims. Visit pakistan.gov.pk for details. This is the raw text that has been imported to the model. Now follow these steps. Step 1, strip white space. Step 2, remove URLs. How do you remove URLs? Re.sub and then write these things in the parentheses and URLs will be removed. Step 3, replace multiple punctuations. How do you do this? This is given in step 3, re.sub, and in the parentheses the command is given. Step 4, the lowercase. Now how do you do this? It is step 3 dot lower and in the parentheses your text. Step 5, replace numbers with num placeholder, NUM placeholder. And how will you do it? It is re.sub and the command in the parentheses. The next step, step 6, is tokenize. How will you tokenize it? The final token is equal to word dash tokenize and the step 5 in the parentheses. This normalized token list is now ready for downstream analysis. Every character is in lowercase, numbers are replaced with num, the URL is replaced with URL, and multiple exclamation marks are reduced to 1. The text is clean, consistent, and machine readable. Now, let's apply the stemming through the Porter stemmer. Again, we will use NLTK's implementation of the Porter stemmer, the same algorithm that has been standard in the information retrieval since 1980. Now import stemmer, import Porter stemmer from NLTK. And how do you do this? Piece is equal to Porter stemmer in the parenthesis the text. Give test words, for example, running, runs, runner, rain, happiness, happy, happier, happiest, teaching, teacher, taught, generalization, generalize, general, and generous. Now for words in the test words, give this command. I want you to pay close attention to what this output tells us. Notice the successes: running, runs, and teaching, all correctly reduced to run and teach. Now notice the failure. Rain does not reduce to run. It stays as rain. This is the classic understemming problem with irregular forms. The Porter stemmer works by suffix stripping and rain has no predictable suffix to strip. Most strikingly, general reduces to general, but generous reduces to gener, a different stem. So a system using Porter stemming would not group these two together, even though they share the same Latin root. Let's apply the lemmatization using NLT's WordNet lemmatizer, which uses the WordNet lexical database to find correct lemmas or base forms. From NLTK.stem import WordNet lemmatizer. The command is given here. How do you import it? Now there is no parts of speech tagging, but lematizer assumes nouns by default. The word in running: rain, bitter, tart, mice, children. Now print word less than 20 and the whole command. Give this whole command. Without a POS tag, the lemmatizer assumes every word is a noun. It correctly lemmatizes mice to mouse and children to child because these are irregular noun plurals that appear in the WordNet lexicon. But it fails on the verb running, rain and tart because when treated as nouns, they have no known inflected forms to normalize. So they are returned unchanged. Now let us provide POS tagging to get the correct lemmas. For POS tagging, give this command or run this command: running wordnet.verb, rain wordnet.verb, better wordnet.adjective, and tart wordnet.verb, mice wordnet.noun, children wordnet.noun. So when you run this whole command, the results are now linguistically correct across the board. Running and rain both lemmatize to run, tart lemmatizes to teach, better lemmatizes to good, and all these are correct forms. This demonstrates the critical importance of providing parts of speech information to lemmatizer. Without it, you get partial results. With it, you get linguistically precise lemmatization. Now let's put everything together into a complete reusable text processing pipeline. We will apply it to a passage from Pakistani newspaper in English because this is the kind of text many of you may work within your research. Look at this command. Text the first command, then text the other command, and then text the other command. And then we have a command for token, and then we have a command for stop, again for token, again for parts of speech tagging, then for lemmatizer, and then for the different words in the POS tagging. Which one is verb, which one is noun, which one is adjective. Now when you run this command, the pipeline has reduced 115 original words to 57 meaningful content tokens by removing stop words and punctuations. Those 57 tokens contains 50 unique lemma types, the core vocabulary of the passage. Look at what the lemmatized frequency profile reveals: school, education, billion, demand, teachers. This is exactly what the article is about: education, funding, school construction, and political demands. Compare this to what a raw word count would have given you: schools and school counted separately, missing half of the occurrences of the core concept. Lemmatization makes the frequency profile more accurate and more interpretable. Now, if you have your own text sample, paste that paragraph and run the whole pipeline function on it. This will give you interesting results. And this is how you can apply it. But for this, you need to understand and learn Python, which is not that difficult. Thank you so much for watching this video. Thank you.